Welcome to the Permaculture Design course for May 2016 lecture on water. And this is the view from my place in Hawaii. So this is the hot tub, wood-fired hot tub at my place in Hawaii. And this is a little water feature that we built just to make a pleasant place with the sound of water. This is a little solar-powered pump and some plants to keep the water clean, and a smooth rock from the beach to run the water across. Very easy to make these kinds of water features, and then these can be harvested and used for mulch, and they grow back very quickly. Water plants are very productive, and then there are small fish in here that keep the mosquitoes down. So again, going back to the slide from the class on ethics, that there's an issue with potable water, and that for less than about 3.5 million people die each year from easily preventable waterborne illness. Most of them are children. Solving this problem would cost less than what Americans spend on bottled water each year. So we could solve this problem forever for what people in America spend on bottled water each year. This is how the water cycle works. There are these huge systems that purify and cycle the water all around the planet, and this has been going on for billions of years, powered by solar energy, and run in self-organizing, self-regulating way. We don't have to manage it, fortunately. And what happens here is that the water evaporates over the oceans by the sun. It evaporates from the land, from bodies of water on the land, from most importantly vegetation on the land, and it evaporates from a variety of sources on the land, and then it rains back onto the land and back onto the ocean. Some of that rain falls down, and some of that runs off. You can see what percentage here, roughly third, a little bit more than a third. Some of it infiltrates into the ground, and some of it's stored in water. And this shows the relative amount. Look at how much more is evaporated from the ocean: 320,000 versus 60,000 square kilometers of water. And so this shows what the water balance is, and this should all balance out. The water that evaporates is eventually going to be the water that is dropped down on the land again. And we're all connected by this. The water that's in your blood, because this system has been going on for such a long time, was once in the blood of dinosaurs. Once ran on all the mighty rivers on the planet: the Mississippi, the Ganges, the Nile, the Amazon. We're all connected. This is what a functional landscape looked like in the Midwest, a hydrologically functional landscape. One that managed and processed and purified water in the way that nature intended here in the Midwest. This is a prairie landscape, and this is what prairie plants look like. You notice they have very deep roots. Some of these roots are as big as 10 meters or 30 feet. Now these little plants right here, these are the imported grasses, the cool season grasses. These are what are called warm season grasses. They don't get their start until it gets really warm in the spring. These are cool season grasses. They were imported from Europe and other places, Asia, and they get started earlier, but they don't do much to build carbon in the soil. They don't do much to create channels so that water can infiltrate and be stored in the soil. They're almost like a green carpet on the surface of the land. These big, deep roots of these prairie plants, when these plants die off, or when they're grazed off by buffalo, or when they're mowed down by fire, or they're physically cut down, and fire was a way in which native people managed the landscape here in the Midwest, and fire is also a way, and it occurred naturally with lightning strikes and things like that. But the prairie ecology evolved with fire and requires fire requires fire to allow some seeds to germinate. It requires fire for its good health. It requires fire or grazing animals to create these fantastically deep, rich soils that we have here in the Midwest. What happens is when these plants get grazed off by one of those factors I mentioned earlier, then they don't need all this root anymore, so some of this root dies off, and it pumps carbon into the soil, which creates food for microbes. It creates it stores carbon in the soil, and it also creates channels in which water can infiltrate. So permeability is really the key to, meaning getting water to sink and be absorbed in the landscape rather than running off, is really the key to holistic water management in any landscape. So an acre of land can absorb about 16,500 gallons of rainfall for each % of organic matter. So permeability and organic matter go hand in hand. This is about 6/10 of an inch of rain. Original prairie landscapes had 10% organic matter and could therefore absorb 6 inches of rain before runoff occurred. The 100-year storm for Iowa is about 7 inches in 24 hours. So runoff was really rare on historic landscapes, and the hydrology was infiltration-based and groundwater rather than runoff-driven. Now we've got a hydrology that's runoff-driven and surface water-driven. Due to conventional tillage agriculture, Iowa soils typically only have 2% organic matter these days, thus the runoff and erosion problems on conventional Iowa ag land. Yet another reason that we need to we need to really pursue perennial crops that we plant once that stay on the soil, stay on the ground, and keep doing those ecological functions of creating permeable landscapes, and rotational grazing again, which helps to create that permeable landscaping when it's done properly, like happened with the prairie and the buffalo, and regenerative agricultures, that as the agriculture system is used and grows and develops and matures, it creates a more rich and holistic hydrology. When we're constructing systems, it's okay to use some heavy machinery and fossil fuels. These kind of systems, the swales, other kind of earthworks that collect and store water in the land, they're going to last for hundreds of years. And so if we use a little bit of fossil fuel and you use a little bit of heavy machinery, it's maybe not such a bad thing. It's that transition ethic that's talked about in the permaculture book that we're using, Practical Permaculture. And they talk about, if during the transition, if you're going to use something that requires a lot of energy but it's going to last a very long time, then maybe that's not a bad trade-off to make in the transition so that we can get there quicker. So what we're doing with water in the landscape is, we're trying to set up systems that capture and store that energy, that we can think of that water as having, clean water particularly, as having a certain order and a certain energy to it, because it's going to take energy to clean that water up. So from Bill Mollison, how can I best use energy before it passes through my site or system? Our strategy is to set up an interception net from source to sink. This net is a compound web of life and technologies and is designed to catch and store as much energy as possible on its way to increasing entropy. Remember, we said every time energy transforms, it transforms in a particular way so that it becomes less useful, and that loss of usefulness is called entropy. And so we want to use it as much as possible because entropy is kind of inevitable, and so use it at the highest and best use each time. So we take very clean water, use it for the purposes we need clean water for, and then we can run that water through another cycle and another cycle and another cycle before it eventually leaves our system. Here's a great way to make landscapes more hydrologically functional. If you don't have prairie lands, if you can't plant prairie plants on it, even with planting prairie plants, this is a good thing. And it's a very simple concept. It's called ripping on contour. So what you do is you find the lines of equal, where it's equally at the same elevation, and you take this machine, take a tractor, and you pull this machine through the earth. So these shanks, these plows really would be under the ground, maybe 12, 18 inches, And what they would do is they create these channels under the ground in which water can be can infiltrate and be stored. And they also create channels in which these channels a little bit of you know, organic material and seeds and things like that will fall in, and these will help to regenerate and create a hydrologically functional landscape. So soil ripping is a really great first step to do on, particularly on broad acre permaculture sites. Swales and diversion drains. So what this is a little, again, this is a very simple concept. A swale is simply a ditch on contour. So you lay out a line. We'll show you how to do this on one of the hands-on days. You lay out a line across the slope that's at the same elevation. So when you put the water in, it doesn't have a tendency to flow out either side. It just sits there. And then what happens is you put these in one after the other on a slope here. So there'd be one here, and maybe another 20 or 50 feet. There'd be another one and another one, so that when it rains, these collect the water and hold the water before it can be lost from your site, can go downhill from your site. And so then what you can do is plant the downhill side of the swale, and there's going to be water. When it rains, this will have water in it, then it'll drain out and it'll be infiltrated into the ground, and then you'll automatically water the plants that are on the downhill side of this swale. And then sometimes these swales can even be used as paths, filled with mulch and used as paths. So this is typically the way it's dug is, that this original slope went on this angle like this. So you just take this part and dig it out and put it on the downhill side. See that? And then in urban landscapes, so how can we take urban landscapes, these really very hard surfaces, pavement, building, roofs, how can we take those and make those hydrologically functional? And one technique is bioswales. We can also make permeable pavement, permeable parking lots, so that when the rain falls down, it doesn't run off, it sinks in. And here's a bioswale. So what happens is, at these hard surfaces, this might be, at the center of a parking lot, so you could park here, and the water would flow in here. Rather than having a curb, you have a way in which the water can flow in. And so it enters the bioswale, and then it slowly seeps into the soil, and you've got plants here that help purify the water, cool it down. And then the water slowly filters through the roots of native plants, where a majority of automobile pollutants are removed, so the pollution is removed. And then the water enters a secondary filter, usually sand, gravel, or rock, and then from there, it slowly makes its way back to the aquifer. So rather than very quickly rushing off, full of a load of pollutants and nutrients, and then just being dumped right into a stream or something like that, you can use these bioswales to infiltrate. Here's another example. So you have a street here, and then you have curb cuts. So if there's a curb here already, you would cut the curb so that when the rainwater hit the street, it would. This one looks like it's in the center of a street, and then this is set, rather than being up on a mound, this is actually below grade. This is actually lower, and it's engineered to have a certain type of soil here and some gravel and things like that here, and then in very, very high rainfall situations, rather than flood the street, you have a way of taking that water. But those rainfall events are pretty rare, and so most of the rainwater, 90-95% of the rainwater in a year, will infiltrate into the ground rather than running off. So here's some examples of that. This one is actually at Come and Go, and Come and Go actually has, this is the Come and Go service station in Fairfield, and it actually has 3 bioswales. Here's the one that's out front, and you notice here's the street, here's the sidewalk. You notice this is lower. This is at a lower level, and I think it's got a beauty and elegance to it. And then here's where you fill your car up. Let me see if I can. Oh, I can't move that. No, never mind. And then maybe you spill a little bit of gasoline. It comes down here into this. Goes through these rocks and into this bioswale and gets cleaned up and then gets infiltrated into the ground. Here's another example. I think this is in Seattle, and you can see this is after a pretty heavy rainfall event. You can see the curb cuts here, where the water comes in and infiltrates. And again, there's no reason why these couldn't be edible and useful plants. And here's again an example of a street where they made the street kind of wavy to slow traffic down, and they put bioswales on both sides and rain infiltration technologies. Here's a beautiful amphitheater. It's also a rain garden. It collects the water from these hard surfaces, and these surfaces could also be permeable paving. And it collects it and infiltrates it. So now let's talk about domestic water supplies. So how much water does it take? In domestic water supplies, I mean, what you use water for in a house or an office, for personal human use. So how much water? A bath requires, maybe 50 gallons. Shower, 2 gallons per minute. So 10-gallon shower is 10-minute shower is 20 gallons. 5-minute shower is 10 gallons. Teeth brushing, 1 gallon. So you can just look through here and you can see, how much water it takes to for each of these various uses. And we have clothes washing machines now that use a third the water and half the energy. And we have 1.6 gallon flush toilets and even less. So the total water per capita for all uses, it varies from about 100 gallons per person per day to about 600 gallons per person per day. And sources for domestic water supply, can get rainwater, naturally distilled, delivered, democratically for free on your rooftop. Ponds and rivers, surface water, springs. We can sometimes underground aquifers come to the surface, and you can get water from springs. Wells, we can dig a hole in the ground down to an aquifer and get water. An aquifer is simply a place where water is stored kind of deep in the ground, and it's typically very clean and pure water. And except some of them have minerals in them. There's various different ways in which aquifers can get polluted, but generally it's very clean water. And then what are called reticulated systems, which are the city water, the pumped water that you get from a pipe from the city. And this is kind of in order of preference. So first you want to go with rainwater if you can, then ponds and rivers, then springs, wells, and finally the most expensive and the probably least quality water is from grid supplied water. And also with energy considerations, it takes a lot of energy to purify and pump and put in the systems, the pipes and everything that deliver water. So this is in rainwater typically hits the surface of your roof. You can collect it at a high level, and many times you can provide that water to whatever you need it for without a pump, because you can collect it at a high level. Whereas in ponds and rivers, you might have to use even an electric pump or a solar powered pump or even water powered pumps. And with springs, again, each one of these has a little bit more energy consideration. So let's look at how much water we can get off a rooftop. So the first thing you need to do is calculate the square footage of a building. And what you're looking at is the building footprint. It doesn't matter how steep the roof is. A flat roof or a very steep roof collects the same amount of water. It's really the square footage of the building. And then one way to do this is to calculate the volume of a box of rain. So if you have a building footprint, let's say you have a building that's 2,000 square feet. So it's going to collect the rain that falls on 2,000 square feet. And let's say you have a foot of rain. So there's going to be in a year, there's going to be in effect a box of rain that hits the surface of that roof that's 1 foot deep and 2,000 square feet in size. And so you can then use that to calculate. And again, I'm kind of waving my hands a little bit here. We'll use an example. Or another way is just to use a rule of thumb that 600 gallons of water is available for every inch of rain that hits 1,000 square feet of roof, or 0.6 of a gallon of water per square foot of roof per inch of rain. So for example, if you had 1,000 square foot roof and you got 10 inches of rain, you'd get 6,000 gallons off that roof, if that makes sense. So let's use an example. 1,000 square foot house, the annual rain is 36 inches. What's the total gallons of water? So first, let's go to that rule of thumb where it's 1,000 square feet. So in the rule of thumb, we said that every 1,000 square feet gets 600 gallons per inch of rain. So in this case, we've got 1,000 square feet, so we know each inch of rain is going to be 600 gallons, and we've got 36 inches of rain. So we get about 22,000 gallons of water that hits that's going to be collected on that roof over the year. And you can just kind of go through. You can look at this one. If you look at the volume, it's 3 feet of rain, 1,000 square feet. So that's going to be 3,000 cubic feet of rain. Again, that box of rain, 3 feet tall and 1,000 square feet as a surface area. And then the gallons are going to be the volume of water times 7.5. So 3,000 times 7.5, about 22,000 gallons. You get roughly the same answer either way. So you can go ahead and do some calculation here if you'd like. What's the annual volume of water that hits the surface of the new SL building, which is about 7,000 square feet, or the old SL wing about 20,000 square feet. So in this case, this would be 7 times 600, or 32,000 gallons seven times 600 times 36 inches. So 7 times 600 times 36 inches. So it'd essentially be 7 times the size of this one, because this is 1,000 square feet. So it'd be about 140,000 gallons a year. And we do have, a very adequate supply of water from rainwater, even though, hundreds of people come every week and fill up their water jugs because they feel like the quality of the water in the SL building is better than quality water they get anyplace else. Now the old SL building, 20,000 square feet, it's actually really huge amount of water. So you look at that, it'd be 20 times 600 times 36, or 20 times about 400,000 gallons of water that hits the surface of the SL wing, or the west wing of the library. So you could. I'll let you go ahead and do these calculations if you want. And here's the rainwater systems that supplied me with agricultural water for my greenhouse at my old straw bale house. So this is a straw bale barn, which is quite large. Collect water off that and store it at a fairly high elevation compared to the rest of the property. You can see here's the gutter, and here's a pipe coming down from the gutters from both sides that puts it into this tank. And this tank feeds it by gravity to this tank, and then I use a pump to pump that into my greenhouse. Another consideration in rain catchment is roof washers. So here are what you want to do is you want to have some device that throws away maybe the first 50 or 100 gallons of water that flows off a roof, because that'll be all the dust and kind of bird poop and various other things like that might be on the roof, and also maybe leaves and things like that. So here's an example of roof washer where you've got a situation where this has a weight. This little bucket has a hinge here and a weight on it, and when it first starts to rain, this is going to fill up, and it's going to flip this way. Once it gets full of water, it'll flip this way, and then the water drains out very slowly. So then the water will then, rather than going into this little bucket and into this small barrel where you just put the wastewater, the first few gallons, it'll then flow into here and fill up the main rainwater tank. And this system works in a very similar way, where you have a sort of a weighted device with a bucket here, and once the bucket gets full, then it'll allow this to drop water into the rain catchment tank. Here's a friend of mine who uses a $5 composting toilet. This is just a bucket. It's from a book called the Humanure Handbook, and we'll talk more about that when we do a lecture on how to purify, how to handle human waste and purify wastewater. And what he has here is rather than have a electric pump, he's off grid, and rather than have an electric pump, which he could easily run with his solar system, I designed and installed the solar for him. He decided to use a system where he actually pumps water into a tank that has an air bladder in it. So as he pumps the water in, it compresses the air in this tank, and he can store pressurized water. He can store 60 or 70 gallons of pressurized water. So he sits here in the morning and he reads a book or plays a game, and he pedals this device here. And what this does is it's a little bike that pedals a water pump, and it takes water from his rainwater cistern and it pumps it into this, maybe 60, 70, 80 gallon tank that has an air bladder inside, and the air, as the water's pumped in, the air gets compressed like a big balloon, and it pressurizes the water. So all the rest of the day, he has 70 or 80 gallons of pressurized water. If he uses more than that in a day in the house, he has to go back and pump it up again. But he likes to do this. He prefers, he likes to get the exercise for this, and an electric pump would be much easier though. And this is part of the system that collects his rainwater and the overflow that goes to a pond. So there's huge amounts of water that flow, that hit a landscape. 36 inches of water on 1 acre, which is what we get what we get here in Iowa, and compare that to San Diego, which gets about 10 inches, and maybe Maine, which gets about 40, 45 inches. Typically, as you go across the country, it gets drier and drier and drier. So it's wetter on the East Coast and drier, a little bit drier in the Midwest, and drier yet again in Nebraska, drier again in Colorado. And Iowa is about the last place into Nebraska where you can grow corn in the summertime without extra irrigation, just from rainfall, because it gets too dry as you go west. So 36 inches of water on 1 acre equals 1 million gallons. So we get about 1 million gallons per acre. So Abundance Eco Village, which I designed, 15 acres, gets 15 million gallons of water for what will eventually be about 60 people, or 15 houses. 30 houses or 60 people, and that's plenty of water. 15 million gallons. The MUM campus, 300 acres, times 1 million gallons per acre. 300 million gallons of water hits the surface of the MUM campus. Fairfield, 3,000 acres. 3 billion gallons of water hits the surface of Fairfield every year. Jefferson County, 250,000 acres times 1 million gallons per acre. I can't even do that in my head. And the state of Iowa, 33 million acres times 1 million gallons. It's huge. I mean, the amount of water that hits the surface of the landscape is just huge. So how do we store water? So the easiest and cheapest way is to store it in the land, where we talked about earlier, to have permeable landscapes, have lots of organic matter that are going to collect and hold and store that water for your plants. The second best way to store water and cheapest way to store water is in ponds. You can dig 1 million gallon pond for $2,000 worth of bulldozer time. That works out to about a half a cent per gallon. If you're going to then the next most expensive way to store water is in tanks. So, for example, the tank we built at the Eco Village, we've built 2 of these. The first one is 50,000 gallons, and that cost about $25,000. So that was about 50 cents a gallon. And it's the size of a small house. It's a big tank. A 1,000-gallon plastic tank costs about $650, which is 65 cents a gallon. And there's many different types of tanks. You can make them out of concrete or ferrocement, which is concrete with steel reinforcing. Then you can make them out of stone. You can make them out of plastic, fiberglass, or wood with a liner. Here's one that I made for just a couple $100 at my place in Hawaii. And you can notice that we put this up higher than the greenhouse in this agricultural area over here, so that the water would drain by gravity to those. And we have a bunch. This is a pipe that goes back to some buildings where it collects the water off the gutter of the building and delivers it to these ponds. These ponds are just Walmart swimming pool liners that are about 18 feet across. And then this is just very inexpensive fencing, wire fencing, and with shade cloth, and so that the plastic liner will not rub up against or push through the fencing. And this one can hold, 5,000-6,000 gallons of water for a couple $100. And this is full of fish. And this fish fish make the water nutrient rich. We use that as part of the fertility program when we're watering the plants. And then we have plants on top of here that also suck up some of those nutrients, and then we can harvest those plants and use them for mulch and use them for compost, because water plants grow very quickly. You can harvest 90% of the plants on this, and in less than a month it'll be completely covered with plants again. And so it's a great way to create mulch and compost. Here's another tank that's kind of architecturally integrated. This is a metal tank, a corrugated tank, just kind of tucked up against the side of a building with, you see here, the little water pump, and probably this is the pipe that brings the water off the roof into the building, into the tank. This is a solar hot water system I had in my place in Hawaii. We got these solar panels for free. We just put this plastic barrel higher than the solar panels and filled this up from our rain catchment system. And so what would happen here is the water, the bottom of this solar hot water collector was plumbed to the bottom of the tank. The top of the solar hot water collector was plumbed to the top of the tank. And so as the hot water, the water is heated here and rises, it flows into the tank, and when the hot water flows in, the cold water is pushed out to the bottom. So this pumps the water and circulates the water through here and heats it without any kind of a pump. It's called thermosiphoning. This is another, again, water is a critical function in any design, and you want to have many different elements. So this is a pond that we put in Hawaii, and again, has this these plants so that we can harvest them for mulch and compost, and also keep the water clean. So another thing to consider is you want to match the water quality to the task. You don't need super pure water for all the uses in your home. For example, you don't need super clean water to flush your toilet. You don't need super clean water to water your plants outside or wash your car. You don't need super clean water to wash your clothes. And so at the Eco Village, we actually have two different water systems delivered to each house. One comes off the roof, goes into a concrete underground water tanks, kept quite clean, goes through some purification, and then is delivered to the house, and that's for the high grade uses. And then we've got another system that collects water off the landscape, stores it in ponds, and we have on the order of 1 million gallons of water stored in the ponds. And that's delivered to each house, and it's for the outside faucets and for the toilets, and some people use it for their washing machine. And so again, matching the quality to the task that you need. And here's the systems. This is an example of the two different systems. So this is the pond system, and this is a little smaller pond that the water is pumped from the bigger ponds, pumped up through here, so it continually cycles and cleans itself. And then we have other kinds of filtration that clean the water before it's delivered to the houses. And then this is the top of the tank that that stores the rainwater off the roof. So this is the water off the ground that's stored in ponds, and again, we swim in the pond. It has multiple uses. Domestic water purification. So once you get the rainwater in the tank, how are you gonna purify it? So typically you go through some kind of particulate filter that takes out the big chunks, some kind of carbon filter, and carbon has an affinity to a lot of different chemicals, particularly pesticides and herbicides and things like that. Could use some kind of a micropore ceramic filter, and micropore ceramic filters the pores are so small that they actually filter out bacteria and even some viruses. And sand filters that work with biology that develops in the sand that purifies the water, and reverse osmosis. These are all different methods of filtration. And reverse osmosis, again, takes just about everything out. And then once you go through the filtration process, oftentimes you run it by an ultraviolet light, which kills any biological activity that you might not have done already. You want to filter the water first before it goes to the UV light, because if the water has particulates in it, then they could block the UV light, and some of the biological activity could get through. You can also use processes of distillation and pasteurization. Distillation evaporates the water, and then it condenses and it leaves out, the pure water gets evaporated out, and when it condenses, it's pure. One of the problems here is if you have compounds in the water that evaporate out at a lower temperature than the water, they'll also get evaporated out and distilled out. But heavy metals, different things like that will stay in the distillate. Pasteurization, on the other hand, is useful for making sure that water is biologically safe. In other words, it doesn't have any biological pathogens in it. And that's just a process of heating it to a certain temperature for a certain time. And if the temperature is high enough, like 130, 140 degrees, it's a very short time, just a few seconds or a few minutes, and all the biological activity is killed. So this is an example of the system I used at my off-grid house, and it's called a Bergey ceramic filter. So for washing my dishes and for taking showers and for flushing the toilet, I just went through a very simple particulate filter and carbon filter. And then for drinking, I went through another stage of ceramic filters. So these are micropore ceramic filters. They're very tiny pores. And you put water, this is in the top of this device, this Bergey filter, right here. And that's where those ceramic filters are. So you fill this up with water, and by gravity, the water has to flow through those filters to the bottom, and that's where you get your clean water for drinking and cooking and things like that from. Slow sand filters, very inexpensive. You can build them out of 55-gallon drums. And what you have in here is you have a sand layer, and you have maybe some pretty fine sand, and then you have gravel, and you have a way of getting the water out. And so what happens here is that you pour the water in, and it slowly goes down through this sand, and the sand develops a layer of algae and other kinds of microorganisms that help to purify the sand. Purify the water. Water distillation. You can use solar energy to distill water, and here's a very simple kind of still where the sun comes in here, and there's a water here, a bed of water at the bottom of the still, and it evaporates, and because this glass is cool, it's the atmospheric temperature, the water will condense on there, and because it's sloped, the water will flow down the surface of this glass and be collected here in this little trough into a tank. So here's an example of one right here, you can see, and here's the water being collected into this trough. And here's an example of one that's used for survival situations in boats or airplanes that crash, that you can use right in the ocean actually. And then solar water purification using pasteurization takes a lot of energy to boil water. To change water from a liquid at 212 to a gas at 212, it takes 1,050 BTUs per pound. And so you got to put a lot of energy into water to evaporate it. But to heat water, just heat water up, below the boiling point, it only takes 1 BTU per pound to raise it 1 degree Fahrenheit. And so it takes a lot less. You can purify a lot more water with the same energy through pasteurization than you can through purification. Sun also has UV light, so you can use that to purify water by exposing water to sunlight, and a couple of ideas there. Some case studies of my house in the eco-village. I don't think I'll talk you through those now. Maybe we'll do that in class. And that's the end of the discussion about water.